So we'll start with our quick look at the calendar and just talk a couple of logistical things before we jump in and start doing the math. Can get everybody's attention up here. I know you guys are working on math, but stay with me here. We've got a couple of important announcements. So first of all, today is February 2nd. We are going to cover lesson number 4, and we're going to start lesson number 5. There's been a little bit of confusion about like homework and what's due and all that, so I want to clarify now. The homework assignments you find on that other packet, right? But it is not the case that there's only one homework assignment every day. So it is not safe to just do assignment 3 today and assignment 4 next class and assignment 5 the one after that. The homework due dates are listed in this column right here. So for example, looking ahead, February 7th, we can see is when homework number 4 is due, and that's the only homework that is due on February 7th. But then February 14th, both assignments 5 and 6 are due. So typically in a given week, there's going to be 3 assignments due over the course of our 2 days. One day and 2 the other day, or vice versa, okay? Now, the fact is, we are just sort of learning about the system, so I have lots of leniency, and I will give full credit for any homework you show me coming up on Tuesday. After Tuesday, we're going to follow the policy in the syllabus, which says that I will give you full credit for homework that is up to 1 class late, up to 1 class late. But if you don't have it done by the class after it was due, I won't give you credit for it. That's my way of trying to encourage you to do the homework on a daily basis as opposed to letting it pile up and then doing it all in one shot later on. Okay, so that's how we read the calendar. Like I said, we're doing 4 and 5S today. The class number 4 is this thing that says dimensional analysis and ratio and proportion. I think that lesson number 4 here is the most challenging material we will have seen so far this semester. I'm not trying to frighten you. I'm just telling you that we're going to work hard like we've been doing all semester, and we're going to make progress. But there's a lot of word problems in there, and I know that that is tricky for some folks. But I really hope that we can get out of the mindset of saying, I can't do word problems. Everybody in this room can do word problems. If I say you have 2 apples and I give you 3 apples, how many apples do you have? 5 apples. Everybody can do word problems. Some word problems are harder than others, but just like with a lot of other things in life, you can get better at word problems with practice, and that is a bunch of what we are going to do this semester. Teresa?
Can you say that it, section 4, lesson 4, it says supplement?
Yes.
I noticed that in one of the packets I believe you gave us.
Yeah.
So is that all we have for homework before we don't have to do anything else?
That's a great question, and yes is the answer to that question. Let me just project it here. Most of the homework is in the book, but the material that we're doing here in lesson 4 is not. So if we take a look at homework assignment number 4, it says see supplemental problems on next pages, regardless of which edition you have. I don't know, I can't, like my mouse is kind of frozen here. I can't do anything. But if you go to the next page of this document, it will say homework for number 4, and then you do the problems that are just literally typed here. Nothing in the textbook for this section, okay? And you'll see that in a few different places in this packet. All right, I think it finally started to move. All right, here it is, yeah. So supplemental problems for homework 4. So there they are. 8 questions there, another few questions here. Answer key right there. Try not to look at it until you give it your all on the problems. All right, thank you, Teresa. Okay, a couple of other announcement type things, and then we'll jump in. First of all, go ahead and grab one of these bookmarks. They should be sitting on your table. This is the schedule of when the Math Studio is covered by a math faculty member. You're welcome to go to the Math Studio and hang out there and do your work anytime that the college is open, but this is when you will find folks who are there happy to help you on your math questions, okay? They can help with homework, or they can help with studying for tests or quizzes, or any of the stuff that we do in this class, okay? You will see that my name is not on here, but my office is right around the corner, and I sit there a lot of the day, 5 days a week. So I am happy to help. Just because I'm not here doesn't mean I'm not available to you. I am. Okay, if you are a digital type person, take a photograph of this and leave the bookmark on the table. You know who you are. All right, we did that. Okay, and then the last thing is this one-page document. Go ahead and grab it. Near the top, it says homework as assessment. Everybody have one of these? Should be on the tables. Okay, this is something that I encourage you to read tonight or maybe over the weekend. It should take less than 10 minutes of your time, and it is going to propose an alternate way to think about doing math homework, different perhaps than the way you've been doing math homework for the last 20 years of your life. And for some of you, this alternate way to think about doing math homework is going to seem like, oh gosh, that is just so inefficient and it would take me forever in a day and there's no chance I'm going to use it. For others of you, changing the way you approach your math homework might have a huge positive impact on the way that you learn mathematics. And so I would just encourage you to give the 10 minutes to read this one-page front and back article and give it a try. I mean, just give it a try. And if it doesn't work for you, then that's fine. But I suspect it's going to work for some of you. If you have questions about it, I'm happy to chat after class. We're not going to talk about this again during the semester, but I hand it out to all of my classes. I think there's some real value in the approach recommended here in this article. Okay? All right. Thank you for bearing with me. Okay, so let's start doing some math. So, so we're here on page, was it 27? Okay, daily summary. In this lesson, we learn how to use dimensional analysis to do unit conversions and to help us set up proportions and solve application problems. Application problems are word problems. Okay, let's jump in here with number 1. It says gas costs $3.57 per gallon. You fill your car with 12 gallons of gas and then buy some items for $15.35 at the counter. How much money do you give to the clerk? You're welcome to type stuff into the calculator, but before you do, I'd really love for you to write an expression. Write down what you want to type into the calculator and then type it in, and then we will come back together. Through here. Okay, so hopefully we wrote something like this thing right here, right? $3.57 times 12 plus 15.35 equals, and then you get whatever you get. It happens to be 58.19 in this case, right? So we just multiply and add, and it's all reasonable. But let's think about the units that are involved in this calculation. I'm going to scroll down here. And we're going to fill in the units. These are exactly the same numbers with the same multiplication and addition and equal signs, but we're going to fill in some units. So let's start on the right-hand side and go left. 58.19, what are the units there? What are they? Those are dollars, right? Okay, and what about the 15.35? Also dollars. And the 12 is gallons. And then the hard one, we're going to pause on this hard one. The units on the left-hand side have to equal the units on the right-hand side, right? If I said 3 apples equals 3 oranges, okay, 3 and 3 are equal, but the units don't agree. And so, no, 3 apples don't equal 3 oranges. So whatever the units are on the left-hand side have to match the units on the right, which we know are dollars. And there's a single unit that's going to get plopped right there that's magically going to make everything work out to be dollars at the end of the day. That 357 is what? It's dollars. It's not dollars. It's dollars per gallon. It is not $3.50, 57 cents for gas. It is $3.57 per gallon. I'm going to use that little blank line as my division line. And so what happens here? Well, I've got this multiplication, and I see gallons on the top, and I see gallons on the bottom, and what nice thing can we do? We can cancel them, right? Gallons disappear. And so on the left-hand side, I've got some dollars plus some more dollars equals dollars. And that makes total sense. And so this concept here, it's not a complicated one with this example. You guys all did the calculation, no problem. But I think having the units there is going to guide us through some word problems later on today. Okay, let's jump to number 5 here. It says now we change gears and talk about ratios. We'll see that the dimensional analysis techniques from above will help us correctly set up proportions. Dimensional analysis is just this idea of writing the units and canceling where you can. Okay, number 6, ratio is just a definition. Ratio compares two numerical quantities through the operation of division. Ratio is just a division of two numbers. A ratio is often written as a quotient, which is a fraction, like A over B, But you could also write A2B, like the word, or you could write A and then a colon B. For us, we're almost exclusively going to write the fraction way, but in some word problems, you'll see a colon. That just means division. Okay, number 7. Let's solve the following proportion. Definition here, a proportion is an equation stating that two ratios are equal. The basic technique for solving proportions is to multiply both sides by both denominators. Let's have a look at our equation here. So there's the equation. X minus 1 over 7 equals 3 over 5. Some of you in some past math class have seen something called cross multiply, and you are perfectly welcome to use cross multiply here. As long as you do it right, you'll get to the right answer. I am not going to use cross multiply. I'm not going to use that phrase again. I'm going to always think about multiplying both sides by both denominators. For those of us who know cross multiply, it might just sort of seem like witchcraft. It's a magical technique that works to solve proportions. I'm not a fan of witchcraft. I want something that makes sense to me. And multiplying both sides by the same number makes sense to me, right? I can multiply both sides by 17, and that's legal. I can multiply both sides by negative 53, and that's legal. What we're going to do is multiply both sides by both denominators. The process we're about to follow is actually written out here. Just kind of ignore it. We're going to build it again. So we're going to multiply this side by 7 and 5, both sides by both denominators. Yeah. And then we're going to multiply the right-hand side by both denominators, 7 times 5. Okay? It's not clear that that's a good thing to do, but at least it's legal, right? There shouldn't be any question about, the fact that we can do this. All we've done is multiply both sides by 35. But by choosing 7 and 5, both denominators, good things are going to happen. On the left-hand side, what cancels? The 7. Don't multiply 7 by 5. Definitely don't distribute the 7 into the x minus 1. We put the 7 up there specifically so we could do that. So anything you do with the 7 other than crossing it off immediately is heading you down a bad path. And on the right-hand side, what happens? The 5's cancel. That's why you put the 5 there. And so all we're going to do is rewrite what remains. I've got a 5 there. I've got an x minus 1, a little multiplication dot, equals, and then on the right-hand side, there's a 3, and then a 7 just sort of lingering. We need to fix something here. I made a mistake. If it's a plus 1, then it is not a proportion. A proportion is specifically fraction equals fraction. And the technique that we're describing here works when it's fraction equals fraction. If there were a plus 1, we'll put it in and then I'll get rid of it. If there were a plus 1 here, what I would really need to do is think about this 7 times 5 hitting the fraction, 3/5, and also hitting the 1. And when it hits the fraction, we would get the same 3 times 7 that we just got. But when it hits the 1, it would be 35 times 1 would be a plus 35 out here. So same technique works, but specifically I'm talking about fraction equals fraction. It would still work, yeah, and that would still be my process, would be to multiply both sides by the lowest common denominator, both denominators in this case. Okay, so I think we're good here. So Carrie is recognizing I have made a mistake. It's a really common mistake, but this is wrong. What did I omit that I needed to bring in? I omitted parentheses. I need to have right here our parentheses. And the reason we need to introduce parentheses in this problem that didn't have any is that that division line on the left-hand side, it's a grouping symbol. And just by looking at that fraction, we can all see very clearly that x minus 1 is one thing. It is all one thing above that fraction line, right? And the fraction line disappeared because we got rid of that denominator. But it doesn't change the fact that x minus 1 was one entire bag of stuff that was supposed to get multiplied by the 5. So really easy to forget to do that. And if you do, you're going to get the wrong answer. I'm going to play the same game on the right-hand side, even though 3 times 7 doesn't require any parentheses. But for me, safest thing is to just get all of those numerators in parentheses. In this case, I've got extra parentheses I didn't need on the right-hand side. Better that than to forget to have parentheses that you do need. Okay, and then solving the rest of this is pretty straightforward. As Carrie mentions, we're going to distribute on the left, 5x minus 5 equals, on the right-hand side, 21. Yeah. Oh, you're welcome. You're totally welcome to multiply the 5 by the 7. I mean, that gives you a 35, and you have lost the sight of the fact that the 7s can cancel. So there's nothing illegal about what you're suggesting, but it heads the wrong way. Yeah. Okay. Okay. And then we solve this, so we add 5 to both sides. 5x is 26. Divide both sides by 5. And we get x is 26 fifths. Getting an answer that is a fraction does not mean you did the problem wrong. Fractions are your friends. They both start with f. Easy to remember. Fractions are good things. Just because you get a fraction doesn't mean you got the answer wrong. Plenty of questions on the coming tests, and I have fraction answers. It's fine. Totally okay for you to put a decimal. If you prefer putting 5.2, that's fine. That's full credit. But you got to be careful with decimals. Personally, I prefer fractions. If you had an answer and the answer is 1/3 and you put 1/3, great, that's full credit. If you put 0.33, that is not full credit because 1/3 is not 0.33. Agree? How many 3's do we need if we're really going to write out 1/3? Infinitely many. If you put a bar, now it's full credit, right? It's not it's a preference just because it's safer to put fractions, not because fractions are inherently like better or more accurate than decimals. So 0.33 is bad. 0.3 with a bar over it is good. 0.333 with some dots is also good. So that's no, and that's fine, and that's fine. Okay. Whereas fractions, as long as you reduce it, there's no question. Like you got it right. Okay, I think that's fine here. Let's move on to the next page. And we will tackle this word problem together. It says the ratio of male students to female students at GCC is 2 to 3. And that's how we read that little colon, just the word TO, 2. Ratio of male to female students at GCC is 2 to 3. If there are 2,000 students at GCC, set up and solve a proportion to find out how many are female. 2,000 students altogether, and we want to know how many are female. Now, it is quite possible that some of you are doing some calculation in your head that doesn't involve any proportions and gets you to the right answer in some like completely legitimate way. But what I want to do is force us to use proportions. I promise there are going to be harder problems where proportions is a good tool. Let's just try to use proportions on this one, even if some of us can kind of intuit a way to the answer. First, we need a variable. Here it is. How many are female? That's what we're going to let X represent, the number of female students, okay? Notice that the word number is written out. This is all written out in English. X equals the number of female students. It doesn't say X equals females because X equals females is not a mathematical definition. Every X equals has to represent a quantity. Females is not a quantity. So be really explicit when you define your variable. And then we are going to start setting up a proportion. So take a look at this sort of skeleton here. We've got an equal sign in the middle. I got a big blank fraction on the left, a big blank fraction on the right, and then some empty space that we're also going to fill in on both sides. So here's how we begin. We are going to choose to put male students and female students in some order on this fraction on the left-hand side. It makes absolutely no difference what order you pick. You could put male students in the numerator and female students in the denominator or vice versa. Doesn't matter. What does matter is that you write it down. I'm going to ask us all to uniformly pick this. But like I said, it could be upside down and it's totally fine. But you got to write it. Make a choice and then write it. Okay. Now, on the left-hand side, it says female students on top, male students in the denominator, and I've got a 2 and a 3 in some order that we're going to put in that fraction. So is it 2 on the top and 3 on the bottom, or 3 on the top and 2 on the bottom? It's 3 and then it's 2, because the order that's given up here is something very specific. It says male students to female students is 2 to 3. And so the same order that those words appear are the order that the numbers have to appear. So the males are represented by 2 and the females are represented by 3. And so by virtue of this choice that I made here, 3 goes with females upstairs, 2 goes with males downstairs. So 3 over 2. Okay. The units on the left-hand side are females over males, just like we had units of dollars in that gasoline problem. Whatever the units are on the left, we know has to match exactly the units on the right, yes? So what do the units on the right have to be? Females over males. Agree? Has to be. And this is why it's important to write it down in the first place, is that as soon as we write it down, it's going to make filling in the blanks, this blank fraction here, easier. But without a clear sense of which thing is represented in the numerator and which in the denominator, we have very little chance of filling in x's in the blanks. Okay, let's go to our definition. X represented the number of female students. Where does it go? It goes on the top, and it is obvious that it goes on the top because we took 2 seconds to write female over male. But without writing that, it's a coin flip. You might put it on the top, you might put it on the bottom, and you're not going to know. Okay, trickiest part is this last blank right here. What we're supposed to do is put something that represents the number of male students at GCC. There is one number we haven't used yet in this problem. What is it? It's 2,000. It is very tempting to put a 2,000. Don't do that. What does 2,000 represent? It's the total, and that's not what goes there. And the reason we know it's not what goes there is because we took 2 seconds to write the word male, and 2,000 is not representing the male population. It represents all the students. So some of us maybe have a very clear sense of what we're going to put here with an X in it. But for those of us who don't, and it's totally cool, if we don't know what to put here, it's going to have 2,000, but it's also going to have X in it. We used the technique from the other day where we said, just pick a number. Just pick a number. How about I say X equals 7. 7 female students at GCC. And how many male students are there at GCC? Everyone agree? If there are 7 female students and 2,000 students altogether, then the remaining 1,993 must be male students, right? The important thing isn't 1993. The important thing is how we calculated it. What did we do to get 1993? For the numbers here, we did 2,000 minus 7, right? 2,000 minus 7. 2,000, that's how the 2,000 is going to get used. 7 is just a number I made up. What is it really? Generally, it's not 7, it is X. So down here, we're putting 2,000 minus X. So getting that calculation, that 2,000 minus X, is tricky for a lot of folks. But as soon as you pick a number like X equals 7, it becomes trivial how to calculate how many male students remain, okay? It is tempting to just say, oh, okay, it's going to be X and then total minus X, and that's how we're going to tackle every one of these problems. But that's not the case. In some cases, I'm going to not give you male to female, but I might give you male to total, in which case 2,000 is the total, and it would just get 2,000 down here. It wouldn't be 2,000 minus X. There are going to be other cases where it's going to be something like 2,000 plus X. So there isn't just one rule where you can always follow. You just have to really think carefully about what it is you are trying to represent, and having those units written down should help. Okay? All right. So the rest of this page is just kind of a more formal write-up of what we said, but I think we're ready to move on to the next problem. You're going to solve this proportion in the activities. So you will find X, but you'll do that in just a few minutes. And let's try number 14. It says, in the US, a baby is born every 3.2 seconds. Here's how we find out how many babies are born in the US each decade. That's the goal. How many babies are born in the US each decade? So what we know is that a baby is born every 3.2 seconds, or 1 baby per 3.2 seconds. Fair? Ultimately, what we want to do is figure out how many babies are born in a decade. So here's how we go from seconds to decade. We are going to multiply right here by a certain number. If I multiply by 18, does that change the value of 1 over 3.2, or does it stay the same? If you multiply a number by 18, does the number change or stay the same? It changes, right? 2 times 18 is not 2. But there is a single number that you can multiply something by, and it doesn't change. It's 1. 1 is the magic number, where you can multiply anything by 1, and it doesn't change, right? 5 times 1, still 5. 2 times 1, still 2. So the only thing we're allowed to do that isn't going to change the value of this fraction is multiply by 1. Now, if we just multiply by 1, we haven't really accomplished anything useful. So we're going to multiply by a fancy form of 1. Here's what we're going to do. We're going to write a fraction line. And we're going to recognize that we've got seconds here in the denominator. And I don't want seconds here. I want decades, ultimately. So if I'm going to cancel the seconds that are in the denominator, I have to put second in the numerator. Even without filling anything else out, do you guys agree I could cancel the word seconds right now? One's on the bottom, one's on the top. Okay, so I've got seconds there. I want to get to another unit of time, the one that's the closest to seconds and heading towards decades. Minutes. So we're going to put minutes down there. Seconds on top, minutes on the bottom. Okay, next thing is to write the number 1 next to one of those words. You're going to write it next to the one that represents something bigger. Which one represents the bigger thing? Minutes, right? Minutes are bigger than seconds. So I'm going to put 1 minute right there. And then I'm going to put the equivalent number of seconds on the top. 1 minute is exactly the same as 60 seconds. And just thinking for one moment about the value of this fraction right here, 60 seconds on the top is exactly equal to 1 minute on the bottom. Agree? When you have a fraction where the top is equal to the bottom, what is the value of that fraction? It's 1. 7 over 7, how much is it? It's 1. 9 over 9 is 1. 60 seconds over 1 minute has a value of 1 because they're equal to each other. And so I have multiplied here by the only thing that we're allowed to multiply by that wouldn't change the original 1 over 3.2. It's 1, but it's a fancy form of 1. And the reason we put this particular one here is for that moment where we can cancel seconds. Okay, times. Another fraction. Play the same game. I currently have minutes left over. Seconds, I don't even see them anymore. I want to get rid of minutes. Do you want to put minutes on the top or on the bottom to cancel this one? Put it on the top. So we put minutes up there. And then we'll keep running up the ladder of time units. Minutes can go to hours. And we put a 1 next to the bigger unit. Which one is that? Hours is definitely bigger than minutes. And then on the top, we put the number of minutes that is equal to 1 hour. And that's, again, 60. And what can we cancel? Minutes cancels to minutes. There. And we're closer to the answer to this question than we were at the start. We want babies per decade. Currently, we have babies per hour. Right? If I just do multiplication of the numbers, I have babies per hour. We're just going to keep building up. So a couple more fractions here. Times. Fraction line. I want to get rid of the hours downstairs, so I put hours up there. What's the next bigger time unit? Day. Put your 1 next to the bigger one. 1 day is bigger than 1 hour. And then 24 hours is equivalent to 1 day. And then we cancel hours. Okay, I think we've got 2 fractions left. What unit goes on top? Day, trying to cancel the only one that's left over on the bottom. Building up, what's the next bigger unit of time? You could do months. Yeah, let's do years. The difficulty with using months is that it is hard to answer how many days are in a month. Because this month the answer is 28, but next month the answer is 31? 31 next month. Right. So months is a dangerous unit to use because it's not standardized. Okay, so what are we doing? 1 year is 365. We'll ignore leap years, it's fine. And then we can cancel the days, and then we got 1 last fraction. I'm going to try to squeeze this in here. I don't want years. Where are we putting years? On the top. And then what's the ultimate unit that I want? Is decades. That's what we've been after this whole time. Put a 1 next to the bigger thing. 1 decade is the same as 10 years. And then we can cancel years and years. Okay, so I think if we just take a look, oh, thanks. If we just take a look at the units that are left over, what's the only unit on the top? Babies, which is what I wanted. And what's the only unit on the bottom? Decade. So ultimately, babies per decade is what this final calculation is going to give us. So we're going to try typing this in. You can do this now if you want to, but you don't need to. I'm just going to multiply straight across all the numerators first. 1 times, and then we've got 60 times 60 times 24 times 365 times 10. That's all in the top. Divided by, now the only thing that contributes on the bottom is what number? It's the 3.2, because everything else is times 1 times 1 times 1. That doesn't always happen, but in this case, the whole bottom is just 3.2 times a bunch of 1s. Okay. That was given. It said 1 baby every, yeah. Okay, can we count some digits here? Yeah, 98 million and change. 98 million and change. Okay. So in the activities and also in the homework, you're going to see things that say do the, like one big calculation like the baby example. This is the baby example. And this is the idea of the baby example is you just repeatedly multiply by 1 and 1 and 1. Okay. All right, so I think that is good. When you're ready, when you've got everything you need to from this screen, you're going to move on to the next page and see how far you can get in the activities.